We are going to show now this theorem that says that every compact subset K of a metric space X is closed and bounded. Okay, so compact implies closed and bounded. Okay, just to summarize. So proof. So let me show first that it is actually bounded. So let's say we have an open cover of K by balls of radius 1. Okay, this means that for every P, every point of the compact set K, okay, we are going to place a ball of radius 1 on top of it. Okay, so these balls are the points in X such that the distance from X to P is less than 1. Okay, this is the definition. So what are we doing here? For every point P, we place a ball. Okay, and we have many points. Okay, so there's going to be a massive overlapping here. But what is going to happen is that the union of all these balls is going to cover the set K. Okay. Now, because K is compact, that implies that we can cover K with a finite number of balls of radius 1. Okay, so maybe we don't need all the massive overlapping, we just need a few of them after all. That's what compactness means. Let's say, just to give the name, capital N is the number of balls that we need to cover for this finite subcovering, okay? Now, once we know this, I claim that the distance from X to Y for every XY in K, the distance between any 2 points in the set K is going to be at most 2n. Okay, and you would say, why 2n? Well, think about it. The worst possible configuration would be if you have all these balls placed one after another like this, okay? This would be like the worst possible configuration. And in this case, how long is the longest distance that you can cover here would be this one. And this distance is the diameter 2. Okay, times the number of balls. Okay, but of course, we don't expect this is the worst case scenario, but we'll probably be doing better than that. So, but we could even write 2n plus 1 just to be sure. Okay, for sure this is a bound, so this means the set is bounded. Let us show now that K is closed. Okay, to do this, what we are going to do is to show that the complement is open. Okay. All right, to do that, what do we need? So if this is our K, what we need to show is that for every P that is outside of K, we are able to find some neighborhood. Okay, let's call it let's call it V, that is completely disjoint with K. Okay, we are able to do that. If we are able to show that there is a V, a neighborhood completely contained in the complement of K, then we are done. All right, so how do we do this? Now, let's take some point, any point Q that is in K. Okay, and what we are going to do, let's forget about V for now. What we are going to do is to look at the distance between the 2 points. Okay, P and Q, and we are going to take neighborhoods of both points with a radius less than 1/2 of the distance between them. Why? Well, if I do that, then the two neighborhoods are going to be disjoint. Okay, so here we have a neighborhood V and another neighborhood W. Okay, let's go back to the original color. So V is a neighborhood of P and W is a neighborhood of Q. Okay, and we have that V and W are disjoint. Okay, but we can do this for every point. Just let's pick another one. So I could pick some point here. So this, the original would be my Q1. Now I pick Q2. Okay, and I could do the same thing, same trick. And now I get another pair of neighborhoods. Okay, disjoint. And now this would be my W and my V, but because it's getting confusing, let's name them based on the point Q. Okay, both of them. Notice that VQ2 is a neighborhood of P, but I call it VQ2 so that I know that that comes from looking at the distance to Q2. Okay, and then the original ones would be now WQ1 and VQ1. Okay, so let's use that notation. Okay. And this is going to be like this for every point Q in K that I choose. Okay, I will always be able to find these neighborhoods, one for P, one for Q, that are disjoint. But now here comes the trick. K is compact, right? So that means that there exists a finite number of Qs. Okay, such that you see that we have basically created a cover, because for every point in K, I'm taking a neighborhood of that point. That creates an open cover. And now, because K is compact, I can take a finite subcovering and then look at what are the points that originated those neighborhoods. Okay, and then for this, I'm going to have that K is contained in the union. Let's write one by one. The union of the neighborhoods, WK1, WQ2, and so on, WQN. Okay. And that's pretty much it, because what we have done here, so we have our K, and in using these neighborhoods, we have created an open set W. W is the union of all the WQs, Okay. And this is an open set. And it leaves out the point P. Why? Because P was not in any of the WQ. So taking the union of those WQs is still leaving out P. Okay. And remember, we also had the VPs. Okay. We had like so many intervals here, sorry, neighborhoods, right? Of different sizes. So what we are going to do is to define V as the intersection of these WQIs, okay, from I equal 1 to n. Okay, if I do that, I take this intersection, what I'm actually doing here is to define a neighborhood of P that doesn't intersect W, because that's the way we define it. Okay, each of the WQs doesn't intersect the VQs. I just realized I wrote here WQI, but I meant V. Okay. And that's all we need, because we have the VQIs, these are open, okay, and the intersection of open, remember, in general is not open, but because it's a finite intersection, then it's okay. Here, it's very important that the intersection is over a finite number of sets, okay? Otherwise, this would be false. So that's why the compactness here is very important in this proof. Okay, but then we are done, because V is a neighborhood of P. V is completely contained in the complementary of K, okay, because it doesn't even intersect W. And that means that P is an interior point, and therefore K complement is open, and we are done.